Well, hello. Thank you everyone for joining us today and welcome. We are really excited to be able to share with you today our cosmological constraints from the fourth data release of the kilodegree survey. Now, KiDS currently spans 1,000 square degrees, and so we're calling this data release KiDS-1000. KiDS is an ESO public survey. It's a multi-band imaging survey spanning wavelengths from the optical all the way through to the infrared. This survey was designed to study weak gravitational lensing by reserving the absolute best weather conditions on Paranal in order to assemble this survey. And the image that you can see here, what we've done here is we've projected the mass maps that we've made from this survey up onto the sky over Paranal to give you a sense of how much of the extragalactic sky that we have now mapped out with KiDS. Contrary to what this image would suggest, though, the two stripes that you can see here are not next to each other on the sky. One's in the north and one is in the south, and neither of them actually cross the Milky Way. Now, the cosmological constraints that we want to share with you today are using three different probes of the large-scale structure. So our first probe is gravitational lensing, cosmic shear. And this is where we look at the images of background galaxies to see how they correlate with each other. And their shapes are correlated because they've been lensed by the foreground large-scale structure. But we're also interested in how those galaxies cluster within the large-scale structure. And to do that, we're using data from the overlapping Busch spectroscopic survey data release 12. Now, KiDS also overlaps with another spectroscopic survey called 2DF lens that mimics Busch. And so our third large-scale structure probe is looking at how the large-scale structure around the Busch and the 2DF lens galaxies lens the background KiDS sources. So there's a three different two-point statistics, and so we call that combined multi-probe large-scale structure analysis a 3 times 2-point analysis. Now, we know that you guys are all very, very busy people. So what we're going to do today is we're just going to jump straight in with our two headline results. And then I will introduce you to the KiDS-1000 team, who have selected just a few highlights from the 5 papers that support these cosmological results. So without further ado, here are our constraints from our cosmic shear analysis. So cosmic shear allows us to set constraints on the parameter S8 that you can see here on the right-hand side. S8 is a combination of 2 cosmological parameters: sigma 8, how clustered the matter is, and omega m, how much matter there is. We've used 3 different types of statistics in order to extract these cosmological parameters from our data set. And these range from the real space through to the Fourier space. And you can see the constraints we get from them here in blue, yellow, and pink. Now you can compare these constraints to what you get from Planck in red. Now, Planck, of course, gives us absolutely exquisite observations of the cosmic microwave background, which tell us about the universe right after the Big Bang. But if you want to use that data to tell you about how the matter is clustering today, which is what we're directly measuring with KiDS, you need a cosmological model. That model is the flat lambda CDM model with a fixed neutrino mass. So we've analysed our data set with that same model, and these are the constraints that we get, and we find that they are low in compared to what you'd predict from Planck. So that's our first headline result. Our second headline result is our 3 times 2-point analysis. So that's the combination of this cosmic shear result with the galaxy clustering and galaxy-galaxy lensing from the overlapping Busch and 2DF lens spectroscopic surveys. Here are our constraints. Now, when we combine these 3 large-scale structure probes together, it breaks that degeneracy that we saw in the previous slide between these 2 cosmological parameters, sigma 8 and omega m. And you can see our constraints here in red. You can compare them to our previous constraints when we analysed our previous data release, which was half the size, and that's in blue. And you can also compare our results to the constraints from the dark energy survey in yellow, and we get really excellent agreement with them. And I should take a moment here to point out that the dark energy survey results here are completely self-consistent. So the galaxy clustering in that analysis comes from their own photometric sample, whereas here we're using an independent spectroscopic survey to get that galaxy clustering result from the overlapping spectroscopic surveys. All right, so in numbers, the S8 constraint we've got is 0.766 plus 0.02 minus 0.014. That's the same overall precision as Planck for the structure growth parameter for this flat lambda CDM model with a fixed neutrino mass. That value of S8 is 8.3 plus or minus 2.6% lower than the constraints you get from Planck. And as we can see from this 3 times 2 point analysis on the right hand side, that tension that we're finding between our constraints and Planck is being driven by differences in the sigma 8 parameter. So if you compare the red contours with the grey in this right hand slide here, then you can see we agree very well on the value of omega m, how much matter there is in total, but the tension is there in the clustering. So what KiDS is seeing is a universe where the matter is less clustered than you would expect from the Planck constraints. Now it's an absolute great pleasure for me to introduce the core KiDS-1000 team, who are now going to take you through some highlights of the analysis that's behind these 2 key cosmology results. We're going to start with Benjamin Joachimi, who's just picked just a handful of things from our methodology paper that explain how we extract these cosmological parameters from our observations, and he's going to be presenting especially on behalf of Jian Lin, who unfortunately is in the wrong time zone to join us right now. We're then going to move on to the core data products that allow these observations to be made, and that is accurate photometric redshifts, and Luca van den Busch and Angus Wright are going to take us through how they accurately calibrated those photometric redshifts, and then Marika Asgari will take us through some of the null tests that we performed in order to ensure that our shear measurements were robust, and that's going to be on behalf of Ben Giblin, who also sends apologies. Marika Asgari will then carry on to tell us a little bit more about those cosmic shear results I just showed you, and Tilman Troester will tell us more about the 3 times 2 point results I just showed you. There is going to be time at the end for questions, so as you go along, please feel free to type questions in the Q&A box at the bottom. If it's about a specific slide, the numbers for the slides are in the top right hand corner of the screen, so you can add your questions in there, and Konrad, Kuijken and Hendrik Hildebrandt are going to be moderating that Q&A session later. So without further ado, let me hand over to Benjamin Joachimi.
Right, okay, I will tell you a little bit about the modeling of our signals and the error bars. And if we take a look at the sky map again, we will obtain cosmic shear from the 2 KiDS patches that are shown in reddish hues on the map, one near the equator, one in the south. And these patches almost completely overlap with our foreground lens galaxies. They're provided by 2DF lens in the south, and that's shown in green, and by Bosch in the north. So that's where we measure galaxy-galaxy lensing. And then the clustering comes from the large blue Bosch area. So while we do measure our 3 probes in a shared cosmic volume, the reality is a little more complex than the cartoon view we had at the very start. And that's in terms of the actual survey geometries and their respective overlaps. And in addition, the survey characteristics are not constant across the sky. We have variable observing conditions, and you see these in the top panels here in different shades of pink and orange. We have different depth per pointing. And as a consequence, we have got varying redshift distributions, varying galaxy number densities, and even the shape properties of the galaxies will vary across the survey. Now, to test the impact of these complex characteristics and validate our analysis pipeline more broadly, we've created a suite of altogether more than 20,000 mock surveys. And this effort was led by Jian, whose picture you see there. Now, the mocks are based on full sky random field simulations that simplify the overall matter distribution for speed, but they're designed to be accurate in producing the 2-point statistics that we actually measure. And they also allow us to include very realistic survey and galaxy sample characteristics. And we then use these mocks to test in detail how to best extract our signals and how to determine the statistical errors, as well as the correlations between the different probes. And the first important finding is that our Bosch clustering is independent from the weak lensing statistics to very good accuracy, to very good approximation. And this is simply because of the large separate area that Bosch covers. Now, the remaining weak lensing covariance is shown on the next slide. And you see a large square there. It has got about 150 entries on each side. So each is one element. You see these little boxes in there. These correspond to the different tomographic bin combinations that we look at in total. Now here we have colored each matrix element by the term, according to the term that dominates this particular entry. And the main takeaway message from that plot is it's quite colorful. So that means we have a range of contributions that all have to be got right in order to model our covariance matrix accurately. On the diagonal, you see mostly yellow, that is the noise, and that we can model very accurately directly from information that we take from the data. On the off diagonal, we have got red and orange, that is sample variance. So this is due to the finite volume that we observe in the universe. We have got some nonlinear coupling between modes, that is shown in green. And we also have residual uncertainty in our shear calibration, and that makes the gray contributions here. And while we can show with our mocks how the covariance is affected by these different levels of realism that I talked about, so the geometry and spatial variations, we can also see that our default analytic approach to the covariance captures these quite well. And in particular, our S8 constraints that you see in the bottom right there are rock solid, stable under these different choices. It doesn't matter whether we use the mock-derived covariance or analytic formalism, realistic survey footprint or not. We are robust to this. Right, and finally, a quick word on the modeling of our signals. So on linear scales, we use a fairly standard approach for weak lensing and for clustering as well. I'm not going to go into detail on that. The interesting bit is on nonlinear scales, where we have to find a coherent model, and this is also a regime where we have quite high signal to noise, so we need to get this right. For cosmic shear, we use a full nonlinear matter power spectrum that's calculated with HM code. That is a halo model that has been calibrated on n-body as well as hydrodynamic simulations. And this is shown in the top panel. You see it agrees quite well with the perturbation theory power spectrum that we use for the galaxy clustering, that's shown in orange, and also with the widely known cosmic EMU emulated power spectrum, that is the normalization here. And it's accurate to a few percent. Note that cosmic EMU itself also has a few percent statistical uncertainty in there. Now on small scales, we have additional uncertainty because matter is being redistributed by baryonic feedback, in particular driven by AGNs, and the amplitude of that effect is quite unknown. And so we marginalize over this amplitude with a white prior, and you see this prior regime here by the blue shaded region on the right, and that encompasses a range of predictions by various hydrodynamic simulations. Then in the bottom panel, you see our galaxy matter power spectrum that's important for galaxy-galaxy lensing. There we blend the perturbative and non-perturbative matter power spectrum approaches, and we build an emulator for the nonlinear galaxy-based terms. And this hybrid model that's shown in gray in the panel there agrees quite well again with the perturbative approach in orange. Now on highly nonlinear scales, modeling nonlinear galaxy mice is very uncertain, and hence we decide to cull our data vectors such that these nonlinear scales shown in gray here are strongly suppressed. Now, with these choices, and quite generally, we are able to pin down our modeling such that S8 constraints are shifted by less than 1/10 of the statistical error on the S8 parameter. And we've worked very hard to achieve the same level of accuracy also for our data products. And one of the critical ingredients for that is the redshift distributions of our source sample. And we're going to hear about that next from Angus.
Thanks very much, Benjamin. So as we heard from Catherine, in cosmic shear, we're attempting to measure statistical measurements of the coherent distortions of galaxy shapes. And we typically make this measurement using coarse ensembles of galaxies grouped roughly along the line of sight, which we call tomographic bins. Now, an integral part of the cosmic shear measurement process is the accurate estimation of the average distances to these ensembles of galaxies. Now, naturally, we would like to do this measurement, this distance estimate, using something very high accuracy such as spectroscopy. However, as Catherine said earlier, KiDS-1000 is a cosmic shear measurement made up of over 20 million sources dispersed over more than 1,000 square degrees on sky. So naturally, obtaining spectroscopy for the entirety of this sample is simply prohibitive. And we require instead another method for estimating the distribution of redshifts for each of our tomographic bins and thereby their average. So in KiDS, we perform this redshift distribution estimation via a direct mapping of the already available spectroscopic sources to our wide field galaxy sample. And we do this direct mapping in n-dimensional color magnitude space. To do this so-called direct calibration, we assume that there is some coherent mapping between galaxy colors and galaxy true redshifts that we can compute. And we perform this computation using a form of machine learning assisted dimensionality reduction, which is called the self-organizing map, which you can see here on the left-hand side of the slide. So the SOM is a 2D representation of an n-dimensional surface, in our case, the galaxy color space. And here what we've done is we've colored the SOM by 3 sets of spectra, which preferentially probe the high redshift universe in blue, the low redshift universe in yellow, and the intermediate redshift universe in pink. And what this coloring shows you is that you do have this direct mapping of color and redshift in this space, which is shown by the tendency of similarly colored cells to sit near one another in this map. So this allows us to use this mapping to directly weight our spectra and therefore reproduce the color properties of the wide field data set, and then assume that that resulting weighted spectral distribution is a reconstruction of the true underlying wide field redshift distribution. Naturally, though, we want to validate that assumption. And so the way in which we validate that assumption is using a sufficiently complex mock galaxy catalog, mock galaxy sample, which you can see shown at the top of this slide. Now, in previous analyses, we performed this direct calibration using a K-nearest neighbor approach, or KNN, in order to associate spectra and wide field observations. And this resulted in redshift distributions you can see in the upper row of that figure that were accurate enough for previous work. But naturally, with 1,000 square degrees of cosmic shear data, our greater statistical precision motivates us to do better in this analysis. And that motivates the use of a new method, which is based on the SOM. And so you can see the redshift distributions estimated using the SOM calibration method shown in the lower panel, the lower row of that figure. And you can just see visually that they're a much better estimate of the underlying truth, shown by the purple lines better tracing the yellow. However, that improved accuracy comes at a price, comes at a cost. And that cost is that the SOM methods generally is unable to calibrate all of the wide field galaxies due to the way that it discretizes the color space. And this results in a slight decrease in the overall number density of the sources which we can use for our cosmic shear analysis that you can see in the table at the bottom of the slide. But this is counteracted by a factor of 2 improvement in our ability to estimate the tomographic bin mean redshifts. So we're therefore confident that our redshift distributions are an improvement over the previous efforts. And naturally, though, with such an integral part of our analysis, such an integral part of the method, it's always beneficial to have an independent method of validation of these particular data products. And that's what Luca is going to talk about now.
Yeah, we obtained this independent redshift estimate by exploiting the clustering between KIDS and spectroscopic galaxies. The key difference with this method is that we are not using colors, but galaxy positions instead, which allows us using bright spectroscopic reference samples. We then slice these samples in narrow bins of redshift and measure the angular cross correlation with KIDS galaxies, from which we obtain, after some corrections, the black data points shown on the right-hand side. We calibrate the low tomographic redshift bins using overlap with hundreds of square degrees of wide area surveys, and the high redshift tomographic bins shown in the bottom using substantially deeper spectroscopic surveys. This allows us to directly compare to the SOM redshift distributions, which are here shown now in red. And we validate our redshift calibration by fitting these SOM redshift distributions to the cross correlation data points while allowing them to slide along the redshift axis. The signal to noise ratio of the cross correlation redshift is high enough that the best fit shifted SOM redshift distributions, which are now marked by the dashed blue lines, indicate no significant offset between both methods, which is also underlined by the shift parameters in the table shown in the bottom left. This demonstrates the accuracy and consistency of our redshift calibration methodology. Following next is Marika Asgari presenting the shear calibration and the cosmological results.
Thank you, Luca. Our data has gone through a series of null tests successfully, which are listed in this paper, Giblin et al. Here I'm showing one example of it that's looking at the B modes in the data, because from lensing we don't expect to see these curls configurations of the shapes of galaxies. So this was showing our measurement of the B modes in our data, and it's showing that it is consistent with random noise. You can see the p-values written there for the full data set, and also for combinations of tomographic bins. There's a long list of tests in this paper, but I give you some examples of what we tested. So for example, we looked at the purity of the point sources using our optical and near infrared colors, and also tested the PSF model and saw that it meets our requirements very easily. We also identified some instrumental defects, but quantified their effect on our analysis and found that to be negligible. And finally, with a shear ratio test, we connect the shear catalog and the redshift distributions together, and so that our data passes that too. So the conclusion of this paper is that the data is science ready. Now let's see the science. As Catherine showed you at the start, we used 3 sets of 2-point statistics to analyze our data. Here we're showing one of them. This is the 2-point correlation functions of shear. On the top you see psi plus, on the bottom you see psi minus. It is a massive data vector, but it's divided into different panels, and each panel shows the combination of our 5 tomographic bins. On top of the data, we're showing the best fitting model in red. Our model has different components. The first component is the cosmological part. That's the standard flat lambda CDM model, but we also include astrophysical modeling. That's the intrinsic elements of galaxies and the effect of baryon feedback. Also, we add nuisance parameters for photometric, redshifts, and shear calibration uncertainties. And this table here is showing some of the properties of our data, but it's meant for cosmic shear experts. For everyone else, this is showing that the redshift of our galaxies increases with the bin, and also we have a good handle on our shear calibration uncertainty. Now let's look at the results. So here we're looking at our results on this parameter capital sigma 8, which is similar to S8 that you saw earlier, but with a different power. And this power is set such that the sigma 8 is perpendicular to the cosmic banana for each of the statistics. So here you can see on the top row there is the Planck results, and the next 3 are the KiDS results. You see that the size of the error bars in this parameter between Planck and our results are very similar to each other, and there is a 3.4 sigma tension in this parameter. You can follow the results for each of the statistics in one of the panels. So let's look at our tests. So we looked at different impact of different parameters, especially nuisance parameters, on our results. In 5 to 12, we're looking at observational nuisance parameters, and 13 and 14 is the astrophysical nuisance parameters. No surprises here, all the fluctuations are within what we expect. But we did other tests as well. So the other test that we did was to look at the impact of each of the redshift bins on our analysis by removing them one by one. Number 15 to 18 are showing what is the impact of the first 3 bins. And you see that the impact is very small, and that's expected because the signal to noise from these galaxies that are lower redshift is generally lower. And then the last 2 are showing what happens if you remove the last 2 bins, and the shift is larger here. Again, this is expected because the signal to noise is larger for these 2 bins. Nevertheless, we went and did a full Bayesian analysis of and quantified the impact of these, and found that these 2 bins, these last 2 bins, are fully consistent. But interestingly, this test flagged the second bin as anomalous. But since as you can see here, it has no effect on our results, we kept it in. And then finally, we compared our results to other cosmic shear analysis. Here you can see 4 of them in green. The first one is showing the results for the previous KiDS data release, KB450. And then we have the combination of KB450 and this year 1. And then the last 2 are DES and HSC year 1 results. So you can see that our results are fully consistent internally and also consistent with other cosmic shear results. But what's intriguing about this plot here is that all the cosmic shear measurements of S8 are on the low side when we compare them to the inferred value from Planck, assuming a flat lambda CDM. And with this, I pass the mic to Tilman, who's going to talk about our combined probe analysis.
Thank you, Marika. So for the cosmic shear part of our 3x2 analysis, we use band powers. The part of the data vector that's used for parameter inference is our E-modes. These are shown on the upper left panel here, together with the best fit model. The reason for using E-modes in our fiducial 3x2 points analysis is that they allow us to much more precisely cut out scales that you want to discard. For correlation functions, they tend to scramble different physical scales, giving a certain angular scale. For our clustering, we use Bosch DR12 galaxies, and we measure the anisotropic correlation function for those in 2 redshift bins, and then further bin those anisotropic correlation functions in so-called wedges. We bin them according to the angle with respect to the line of sight. So this analysis very closely follows the Bosch DR12 full ship analysis of Sanchez et al. And what's shown here is, again, our data vector for the galaxy clustering. On the left, the low redshift bin, on the right, the high redshift bin for the 3 wedges that we consider. The fit is excellent, even if chi-pi might be misleading here because the data points are very much correlated. For the last part of our 3x2 point data vector, we use galaxy-galaxy lensing. For the lenses, we use the same galaxies as for the clustering. So we use the Bosch DR12 galaxies in 2 redshift bins. That's shown at the left-hand upper left panel. And also include the 2DF lens galaxies for the galaxy-galaxy lensing in the same redshift bins. The source galaxies are the same as for cosmic shear. So again, you have the 5 tomographic bins here, and these are shown, the redshift distribution here is shown on the left on the bottom panel. The resulting measurement, the data vector shown on the right. Now, we only use the data points that have a white background here and discard everything with a gray background. The reason for that is that the bias model that we use for the galaxy-galaxy lensing is the same that we use for clustering, and it's based on perturbation theory. So that breaks down at intermediate scale, so we can't use the small scale information. Now that we have all our measurements in place, so the cosmic shear, the galaxy clustering, and the galaxy-galaxy lensing, we can derive our cosmological parameters from that. So what's shown here again is S8 and omega m. And in pink, we can have the cosmic shear, the band power cosmic shear results that Marika has shown before. If we add on top of that cosmic shear the galaxy-galaxy lensing, we end up with the dark purple contours. So you see that in this parameterization, the constraints are limited, and the reason for that is that we have to discard most of our small-scale galaxy-galaxy lensing information. Where the galaxy-galaxy lensing helps quite a bit is in the intrinsic alignment parameter, which is not shown here though. The galaxy clustering mainly helps to constrain omega m, so the amount of matter in the universe. It breaks the degeneracy that we see here between S8 and omega m, and combining all these probes together, we arrive as our main result, the KiDS-1000 3x2 analysis, is shown in red. And you might ask, how far is that red contour away from the gray contour? And for the one parameter we set out in this whole analysis to measure, which is S8, the discrepancy is 3.1 sigma. It is quite stable for different measures on how you want to measure that tension. Now, if you look at the whole shared parameter space between Planck and our 3 times super analysis, then the tension goes down to roughly 2 sigma, again, quite stable depending on how you measure that discrepancy in a high dimensional parameter space. They're still in that 2 to 3 sigma regime, and it's going to be very exciting to see what DS and HSC find for this. And with that, I'll hand back to Catherine for the conclusions.
Thanks very much, Tilman. So we are reaching the conclusion of the presentation part of our webinar today, but let me just briefly summarize for you. So these 2 highlight results, we're finding roughly a 3 sigma tension in this S8 parameter. Our 3 times 2 point analysis is showing that that difference is mainly driven by differences in sigma 8, so the clustering of the matter. So if you want a 1-sentence summary of our presentation today, it's that the universe is less clumpy than Planck predicts, or at least that's what KiDS is seeing. I hope we've been able to give you some flavour of all of the validation that's gone on behind the scenes here to ensure that this cosmological analysis is very robust. We've been validating our methods using mock surveys, image simulations, null tests, independent spectroscopic photometric clustering analyses. And what I wanted to just briefly clarify is any systematic uncertainties that we've identified during these technical analyses have been folded through as nuisance parameters. So the constraints that you see on the right-hand side there include both statistical and systematic uncertainties. So 3 sigma, it's an interesting level of tension, but that's still a 1 in 1,000 chance that KiDS has just looked at an unlucky part of the universe. So we are very much eagerly awaiting the results from our academic cousins, the fantastic dark energy survey, the wonderful hypersupreme camera survey. We're very excited to see what they also find with their next data releases, because if all 3 surveys, which are independent teams, independent telescopes, independent cameras, if they continue to find these low clustering results that we are seeing at the moment, then that could be the evidence that we need to say that the flat lambda CDM model is missing something in order to explain these differences that we're seeing at the moment between the low redshift universe and the high redshift universe. Before I hand over to Konrad and Hendrik for questions, I just want to say a brief thanks to the KiDS team. You've just seen a handful of kids today. This is us in happier times. We're also having quite good fun in lockdown together through the power of Zoom. And we also wanted to thank our funders, particularly the European Research Council, who significantly funded a big chunk of this research. So I will hand over to Hendrik and Konrad, and we'll see if we've got any questions.
Thanks very much. Thanks to all the presenters for presenting our results so nicely. Thanks to all the attendees for sticking with us. There's a huge number of people online. Plenty of questions as well. The first, I'm trying to group we'll run a question session of about 10-15 minutes, and I'll try to group the questions by themes. So there's one question which is, I think, for Angus. It's about slide 10 from Tassia Ferreira and from John Loveday. It's about the SOM. What are the black cells in the map? And the other question is, can the SOM be more than 2 dimensions?
So the black cells that are shown here are cells that have no spectra residing in them. So these are essentially the uncalibrated parts of the color space that exist when you use a spectroscopic compilation that is not pre-selected to match a cosmic shear sample, essentially. So these are the reason why, when you use the SOM method, you end up having photometric sources that land in cells with no spectra that you therefore naturally can't calibrate. And that's the reason that I mentioned the deprecation in the number density that we saw with regards to, say, using a different method, the KNN, which allows you to have essentially no discretization of the n-dimensional color space. And to answer your question, John, there is mechanisms for making a multi-leveled SOM, that is a series of 2-dimensional SOMs that basically inform slightly different parts of the data set. But in terms of whether there's a 3-dimensional version, not to my knowledge.
All right, thanks, Angus. I'm taking over for the next question. Konrad wants to order those into sections. I have no idea what these sections are because we didn't practice that. So I'm just going to ask a question that I find interesting. That's coming from George F. Stathio. It's about the omega matter constraints between the cosmic shear and the 3 times 2 point analysis, are those consistent? Have you quantified this, and what caused the change? So I guess that's a question for Catherine.
I didn't quite get the question. Can you ask me again, Hendrik?
So the omega matter constraints for cosmic shear and 3 times 2 point, they shift a little bit, and George would like to know whether those are consistent and what causes the change.
In omega m?
So I think that refers to the slide you showed in the beginning with 2-point correlation functions.
Ah. This one. Okay, right. George, are you asking about the difference between the red contours and the blue contours? I think that's maybe what you're asking. Okay, so that's what's happening there is you're seeing the difference between doubling our survey area. So our value for people who have been following KiDS over the years, we have always had a low value of S8. Actually, doubling our survey area has moved us up a little bit. And has also tightened our constraints, and that's all you're seeing here. So we've got this sort of sigma 8 omega m banana, and our S8 value has moved up just slightly, but it's perfectly consistent. We've done analyses of would we expect that with doubling our survey area, and indeed we would. So yes, they are consistent with each other.
Okay, there's a couple of questions on the intrinsic alignment modeling. Whether we can say a little bit more about it, and also in particular from George of Stati, what are the solutions to our intrinsic alignment parameters? Who wants to take that? Marika, maybe?
I think Benjamin was going to answer. He just... Yeah.
Doesn't matter. Okay, yeah, I can take that. So the model that we adopt is the same as we did in previous analyses. So it is a simple effective model that's extrapolated to nonlinear scales. So for the expert, that would be the NLA model. It's based on the linear alignment paradigm. And by default, we use a single amplitude parameter. So this amplitude parameter tells us about the coupling between a projected galaxy ellipticity and the surrounding tidal field of the large-scale structure. And this parameter is constrained to values of order 1. It's fairly stable across the different kinds of analyses that we've presented here today. Now, this model is rather simple, and we also look at an extension, and I think very helpfully that's on the slide that you see now. That's item number 14 there. So there we include an empirical extension, again, has been used before with the power law, and the index of that is free. So you have a free redshift dependence, a smooth redshift dependence. And as you see, that has no impact whatsoever on the constraints, so it's stable. With that, also the goodness of fit does not improve. So there's actually, in a Bayesian sense, there's no reason to extend the model, and hence we keep it simple, as we've also seen in this and earlier analyses, for instance, in Angus's paper. That's becoming quite clear that if you have a lot of flexibility in your intrinsic alignment model, that can very easily then be abused by your redshift distributions to fix little residual problems that might be there.
Right, next question is from Aichiro Komatsu. He's asking, was any part of the cosmology analysis done blindly?
So I can answer that one. Yes, absolutely. So kids have been blinding their data right from our first data release analysis back in 2015. We've now got this to a finely honed system where we generate 3 different versions of our catalogues right from the start. One of them is the truth. 2 are scrambled in a little way that changes the overall constraint, and the resulting S8 that we get changes by about ±2 sigma. So we were analysing 3 kids surveys right up until the 9th of July, when Matthias Bartelmann put us out of our misery and told us which one of the results was the truth. It was a very exciting day. Some of us really wanted the result that agreed with Planck. Other ones really wanted the 4 sigma result, so we wouldn't be in this position of going 3 sigma. But we were right in the middle with the 3 sigma results. I think blinding is really, really important when you have choices that you can make in your analysis, which we can see in this slide here. There are lots of different things that you can switch on and off with your nuisance parameters. And even though it doesn't make a significant difference to our results here, we think doing your analysis of blind is really important when you're checking out things as interesting as this tension. And so we're really pleased that all of the weak lensing surveys are doing that now, and indeed other surveys like ACT and EBOS and things like that. Yeah.
Okay, there's a question from Adam Rees. What level of tension with Planck do you find if you combine with other low Z probes of S8 and even H0? And I think Tilman is the best person to take a stab at that.
Yes, so we haven't combined with other probes yet. That is part of a forthcoming work. Or look at, for example, combining with the new EBOS results and so on, and also other constraints on H or cluster amplitude of clustering of the low redshift universe. But for this analysis, we really only focused on KiDS plus the bus clustering.
Okay. I will ask another redshift related question. That's from Alex Hall. Maybe Marika can answer that. What is the cause of the anomalous N of Z of bin 2?
So we don't know for sure, and this is one of our priorities for KiDS legacy analysis to find out. We have some hypotheses, but it's not clear which one it could be. Like, one could be that maybe there is a small population of galaxies at high redshift in this bin that we didn't detect with the other tests that we've done. Or maybe there are some other objects which are not galaxies and they have contaminated this bin. All I can tell you is that that bin actually prefers an S8 that is higher. So if anything, including that bin will decrease the tension with Planck.
I have a question from Mike Jarvis, but before I pose it, I would also like to say a lot of people are just sending us thanks rather than thanks and congratulations rather than questions. And so I'd just like to say thanks for the thanks. Mike Jarvis asks, and this is a question for Catherine, it's about the shears. The uncertainty in the shear bias for bins 4 and 5 were significantly smaller than the uncertainties for bins 1, 2, and 3. What is causing this difference?
Thanks, Mike. I put this table in for you. We had lots of discussions about whether to put this expert level table in, but it's the type of numbers that people want to know. So the uncertainty on our shear calibration error comes from different choices that we can make with our image simulations. So we have a very detailed suite of image simulations where we emulate KiDS using real galaxies from Cosmos HST imaging. But there are choices that we can make with that image simulation. We can include correlations between the photometric redshift and the size and the ellipticity of the galaxy, or we can remove and erase those correlations, and the uncertainty that you get on here comes from those switching those different things on and off in the image simulations. And those, interestingly, the potential correlations between size and shape and ellipticity affect the lower redshift bins more. And I think that's partially because those low redshift bins have that high redshift tail that I think is the thing that's sort of less uncertain or more uncertain, whereas the bins 4 and 5 are really quite very narrow, and we can measure those galaxies very, very well. So I think that's what's going on, Mike.
Right, we have another question for Tilman from Carlos Frank. What were those unconstrained parameters that reduced the tension to 2.1 sigma?
Right, so the parameters that we sample in are omega c h squared, omega b h squared, h and s and s8. So that's the sample parameter space. So the exit parameter that are basically unconstrained are the baryon density, and at S we have some constraints on omega c and omega h, but those agree quite well with Planck.
Okay, there are a few more questions, but in view of the time, I suggest we leave it here. If you have more questions, of course, do take a look at our papers and get in touch by email or however. Please take a look. All the papers are available on the website now. They will be on the archive tomorrow. I'd like to thank everyone for attending, everyone for presenting, and goodbye.